We just created a simple brute force algorithm that evaluates a polynomial at a point, given the polynomial's coefficients. And we deduced and derived its complexity class and discovered that it's a quadratic time algorithm. Right, so if the degree of the polynomial is n, then it takes order n squared operations, specifically n squared multiplications to evaluate the polynomial. So we should ask, is this the best we can do? So let's go back to our polynomial formula. So p of x here is given by an x to the n plus an minus 1 times x to the n minus 1 plus and then so on. So when we wrote the algorithm, I'll write the last couple terms here. So a2x squared plus a1x plus a0. When we wrote the algorithm, what we implicitly did, and it didn't matter that we did this, but what we implicitly did is we started here, and then we evaluated in that direction. So if you evaluate a polynomial in that direction, you may actually stumble upon something kind of interesting. So let's just picture what happens when we have just completed evaluating this, and then we need to evaluate this. So if I write, and so now think about it like this. I suppose that you know an minus 1 times x to the n minus 1. And now you want to compute an. So we know this. Now you want to compute an x to the n. What is x to the n? What's another way of writing this? Well, I can just as easily write this an times x times x to the n minus 1. Okay, if I take x times x to the n minus 1, that just gives me x to the n, right? This is just an equality here. This is just the definition of exponentiation. And notice that once you see this, you say, shoot, I should have saved the value of x to the n minus 1 that I computed last time. And then to get x to the n, all I have to do is multiply on one more x, and everything is fine. Right? And so every time I write, let's just write ai x to the I, this is always something I can write. I mean, as long as I is greater than 0, this is always something I can write as ai times x to the I minus 1. And as long as I'm evaluating my polynomial in this direction, right, from small degree to large degree, and I have saved this value, then I can save a huge number of multiplications to perform. So let's use this concept to create a new algorithm that saves the value of x to the power from the previous time step, from the previous iteration, and then uses that to compute the next one, so that we don't have to keep multiplying on a huge number of x's as we go down the line here. So I'm going to call this one BF polynomial 2, right? Because now this is a second kind of brute force themed polynomial evaluation algorithm. So BF poly 2 has the same exact arguments, right? So x is the point we're evaluating at. A is the array of coefficients, right? So we're not giving it any more or less information. But now we're going to do this in a different way. So let me define x power, and I'll initialize this just as 1. And this is the variable where we will store the previous power of x. All right, so here we've got x power is initialized at 1. Just as before, I'll initialize my total at the constant term, so a0. And then I'll set up one for loop. Now I only need one, so for I equals 1 to n, so the same thing, we need to have this for loop go over the array of coefficients and then add on a term for each coefficient. So what I'll do is I'll multiply on another x to my x power. So x power times equals x, right? So now I've just incremented the power on my x, and then I'll multiply that onto my my coefficient and add that to the total. So then total plus equals AI times x power, right? So this piece here is where I'm multiplying on an x. So that's times x. This piece here, and then I have to save that. I have to save that x power. I have to make sure that doesn't get wiped out somewhere. And then this is where I multiply on my x power onto my coefficient, and then add that to the running total. And then at the end of this, once the for loop terminates, I return the total. All right, so what's the complexity of this? Well, immediately you can see that we've got fewer operations, fewer multiplications are being performed. And the reason for that is quite simple. It's just that here we have only one for loop, rather than the nested for loop that gave us the triangle, right? You saw the triangle of calls, the triangle of multiplications. Here we have exactly one multiplication. Well, I should say exactly two multiplications per coefficient in the polynomial, and we can, just to be totally complete, we can write down the expression for this, right? So I can say t of n is equal to the sum from I equals 1 to n. And then if I want to be totally complete, I can say, look, on the inside of this for loop, exactly two multiplications happen. So two multiplications, mults. And how does this thing come out? Well, this is just 2 times n minus 1 plus 1, right? Which in the end is 2n. So, 2n is a lot less than even the 1/2 n squared we had on the other one. And in fact, it's a lower order of growth. It's only a linear order of growth. How can I see it's a linear order of growth? Well, there's a variety of ways you could see it. The clearest is that it's just n times some constant, which means that it has a linear order of growth, an n order of growth. So one of the takeaways for this whole problem here, just aside from the fact that I think this is it's a clever little hack. One of the takeaways though is that sometimes you can start with a brute force algorithm that just takes a definition and pushes it through, kind of as simply and crudely as possible. You can take that and you can look at it and be a little tiny bit clever and come up with some significant optimizations. So here we were able to go from an n squared algorithm down to a linear time algorithm, an n algorithm, just by noticing that we were performing too many multiplications. And so this is the main lesson here. And then on top of that, it gives us the ability to actually look at some pseudocode and drop that into an expression and then derive the order of growth.